everybody. My name is Leonardo Quattrocchi. I am a mechanical engineer, graduated from the Sapienza University of Rome many years ago. I worked for about 40 years in various industrial sectors, from mechanics to food, from electronics to software. I currently teach management of advanced technologies at Lewis Business School, and I follow for Sistemi Formativi Confindustria the European project New Metro on future learning of mechatronic technicians.
A system is a set of elements, components, subsystems that interact with each other so that the system itself carries out a specific purpose. These elements are interdependent, interconnected, so that they form a whole. They can be things, objects, products, both hardware and software, processes, people, data, techniques, services, living beings, organizations. Interconnections and interactions are the key characteristics which can differentiate elements which are separated from each other from a system. A system, by its nature, has a purpose, a function, or is designed to perform a certain basic task. For example, a family of bees interacting with each other in a complex way to survive and reproduce is a living system. A machine, for example, a helicopter in which the different parts are joined and work together with the purpose of flying, is a system. All the constituent parts work together, and the single components, if taken separately, would not be of much use. For instance, a rotor of a helicopter by itself, not connected to the engine and to the rest of the airframe, is useless. The human body is a complex organization of various kinds of organs, so arranged that together they can perform complex functions for us and allow us to live and reproduce. Our body is a system, since it can autonomously carry out its necessary functions. Since human beings need energy, water, minerals, etc. as inputs, the human body is an open system with outputs as well. While, on the contrary, a system which has no inputs is called a closed system. Examples of closed systems are a lithium-ion battery or a chicken's egg. Going back to our bodies, they are made up of major subsystems such as the skeletal, nervous, cardiovascular, lymphatic, etc., which are improperly called systems but are in reality subsystems, since they exchange matter and energy with other parts. And they could not live independently from each other. In other words, our nervous system, for instance, could not live by itself without its interconnections with the other parts of our body. And similarly, the water cycle is a system. The water cycle has no starting point as such, but if we start from the oceans where the majority of water is, the sun heats up the seawater. Some of it evaporates as vapor into the air. Rising air currents take the vapor up into the atmosphere, along with water transpired from plants or animals or evaporated from the soil. The vapor rises into the air, where cooler temperature causes it to condense into clouds. Air currents move clouds around the globe. Cloud particles collide, grow, and fall out of the sky as rain. Some precipitation falls as snow. Snow in warmer climates often melts when spring arrives, and the melted water flows over land. Most precipitation falls directly back into the oceans or onto land, where, due to gravity, flows over to the ground as rivers moving towards the ocean. Some water accumulates as fresh water in lakes. Water also soaks into the ground, and sometimes it finds openings in the land surface and emerges as freshwater springs. Over time, though, all of this water keeps moving, some to re-enter the ocean, where the water cycle ends, or better, begins. Looking at this scenery, could you tell what is happening? What do we understand when such phenomena occur. What do we understand where lightnings strike? Would we been able to understand all of the complex water cycle simply by looking at the component of the system, such as a lightning? Or observing and examining, even in all its minor and microscopic details, a single raindrop? As Peter ENG of MIT, one of the leading figures in systems thinking, writes, when cloud masses increase in number, the sky darkens, leaves twist upwards, we know it will rain. We also know that after the storm, the runoff will feed into groundwater miles away and the sky will grow clear by tomorrow. All these events are distant in time and space, and yet they are all connected within the same pattern. Each has an influence on the rest, an influence that is usually hidden from view. You can only understand the system of a rainstorm by contemplating the whole, not any individual component of the pattern. And the rainstorm is part of the water cycle system that we saw. And the water cycle extends its influence on all living creatures on Earth, a very complex interconnection. Since everything is interconnected, there are constant feedback loops and flows between elements of a system. We can observe, understand, and intervene in connections and feedback loops just to understand what is happening and complete the understanding of their type and dynamics. You surely know this famous sentence, when a butterfly flutters its wing in one part of the world, it can cause a hurricane in another. In popular culture, the term butterfly effect is almost always misused. It is credited to Edward Lorenz, who was a famous meteorologist and mathematician. During the 50s, Lorenz searched for a means of predicting the weather, as he found linear models to be ineffective, as we also see these days when rarely weather forecasts are accurate. The butterfly effect has become synonymous with leverage, the idea of a small thing that has a big impact. This misses a bit the point of Lorenz's insight. The reality is that small things in a complex system may have no effect at all, or a massive one, and it is often very difficult to know which will turn out to be the case. Let's think, for instance, to the current dramatic situation we are in the world today. A bat in China is causing so many disastrous and deadly effects. This is the original mathematical enunciation of Lorenz, subject to the conditions, continuity, but it's too complicated. In simpler language, he theorized that the weather prediction models are inaccurate. They are so because knowing the precise starting condition is impossible, and a tiny change can throw off all the results. To make the concept understandable to non-scientific audiences, Lorenz began to use the butterfly analogy. Understanding feedback loops is about gaining perspective of causality, when one thing results in another thing, in a dynamic and constantly evolving system. All systems are dynamic and constantly changing in some way. That is the essence of life. And systems thinking and mechatronics are at the heart of this way of thinking, as we will see better in our next lesson. Thank you.